Hello, in this talk I will speak about the basics of molecular dynamics. The first thing to distinguish is the type of model we have. The simplest model that was also first simulated in 60s, I guess, was a system of hard spheres, like billiard balls. Such spheres move on straight lines through space and collide once in a while. The simulation algorithm in this case must calculate or predict the next collision, and after a collision occurs, it recalculates the trajectories, which are straight lines. But this is a very simple system and it's not too much useful for chemistry. In this course, I will cover mostly the so-called classical molecular dynamics, which is based on the integration of the equations of motion. That is, we have forces. Forces are given by gradients of the interaction potential, or the potential energy surface if you wish. If we have n atoms, we have 3n components of forces. In addition to this, we can sometimes add something else to these forces or to these forces. These may be different types of random forces. They are useful to mimic, for example, a solvent which we don't want to have explicitly, or to provide coordinate dynamics and so on. Again, at this moment, I will speak about the integration of the equation of motion of smooth enough potential so that we have gradients. That is, first we need these forces. The simplest example of a force field, you can imagine argon, is that the interaction energy is a sum over pair contributions of pair components. Without too much formal mathematics, the force acting on one particle I is a sum over all surrounding molecules, that is, we'll sum over J, which goes over all molecules except I. The particle doesn't interact with itself. And after doing the calculation, we'll find that a net force acting on particle I is a sum of these pair forces, and each of these pair forces is in the direction of a vector between these two particles. A normalized vector between these two particles is given here. It is the vector divided by its value, and this is the magnitude of the force. This is the direction, so this is the final formula. Okay, we have the force field, we can calculate forces, and what to do with it. We have the Newton's equations of motion that you know from physics. These Newton equations of motion relate the force acting on particles, that is, this is a vector on particle I. The subscript I goes over all atoms. And if we divide this force by the mass of the particle, we'll get the acceleration. I will use two dots to denote the second time derivative. We will solve this equation numerically by the method of finite differences. That is, we need a time step, certain time step that will be short enough but not too short so that our simulation is not too slow. From the mathematical point of view, this is the initial value problem. We also need to know the positions and velocity at certain initial time t0. In the textbooks of numerical mathematics, perhaps you had a course about numerical mathematics, we can find many methods how to numerically solve such a set of ordinary differential equations of the second order. Perhaps you've heard about the Runge-Kutta types of methods. They need many evaluations of the right-hand side, and for reasons that I will explain in detail later, not only they are inefficient to be used for molecular dynamics, but also they have poor energy conservation. That is, we usually don't use such methods. Another type of method that you find in textbooks of numerical mathematics are the so-called predicted corrector methods. They are better and sometimes used, but still this is not the method of the first choice. The methods of the first choice are the methods which are called symplectic. I will speak about them. They are designed for this special type of the equations of motion that have certain special structure, and their good property is that they very good energy conservation, essentially the best that we can imagine. That is why we like them. They are also, or at least the simplest method is so simple that it is widely used and good enough. Sometimes we have a system which is quite complex. You can imagine that these forces are the result of many calculations of a force field of many terms. Some terms may lead to fast motion, like vibrations. It may be useful to split the integration into several time steps. We will integrate or calculate the fast motion more often and the rest once a while. These are the so-called multiple time step methods. They are usually symplectic, quite demanding. I will not speak about them in detail, but you should know that something like this exists. The simplest method that is often used, I would say that 90% of all simulations or of all atomistic simulations uses the Verlay method or some type of it, can be derived from the Taylor expansion. I have a particle with position r. Actually, instead of r, we can imagine a vector of the i's atom, but it's not important at this moment. I will use this shorthand notation. That is, the position of the atom at time t minus the time step can be expanded using the Taylor expansion to the position at time t minus, we have minus h here, the velocity times the time step plus the second order term, and at this moment I will neglect all higher terms. Then I will write this trivial equation, and then I will do the same for time plus time step. Again, I have here the expansion that looks pretty the same except for the sign. And now I'll do the calculation which is depicted here. That is, I'll take the first equation once, the last equation once, and subtract twice the second equation. If I do this, I'll get here this minus twice this plus this. This is the numerator. And if I do this, all these terms cancel out, and what's left here is twice this term. So the result is the second derivative, which I know that equals 4 divided by the mass, and it is given by this formula. Actually, this is the simplest formula for numerical evaluation of the second derivative. Also, we have some missing terms here, which are on the order of the time step squared. We will neglect. Our method isn't exact, but the shorter time step, it will be more accurate. So we have the equation in this form, and now I will rearrange this term in such a way that I'll put this to the left-hand side and the rest to the right-hand side. In this way, I am getting the position of particles at time plus one time step in future using this term. This is essentially linear extrapolation from time t and time by one time step in the history to the future, like this is a straight line, and the correction which depends on the forces. If we want to use this in the integration, we must mention that this is not in the form of the initial value problem. I have something here that I generally don't know, but I can calculate it using the Taylor expansion. Actually, it is pretty enough. Just start from this. Okay. What are good and bad properties of this method? First, what we see is that this method is time reversible. Because if we exchange time step to minus time step and just replace these terms, I'll get exactly the same formula. And if my equations are exactly time reversible, I can expect that I will have good energy conservation. I will have no energy drift. It is even better. These methods are even symplectic. I will speak about symplecticity in brief later. But as regards time reversibility, imagine that you have an evolving system which after some time will be in equilibrium. Okay, then I must get the same average values if I reverse the arrow of time, the direction of time. And if this is time reversible, I on average will obtain the same behavior of the total energy in time. I cannot get energy drift because these equations are symmetric. But there is also a disadvantage. In this equation, I don't see a velocity. I can fix it for the initial value. I don't need the velocity on the right-hand side for the original equations of motion. But there are sometimes variants of the equations of motion that need the velocities. We will see such cases later. Then I cannot directly use this method if I have velocities at the right-hand side. There are several equivalent formulations of this method, like Leapfrog, that I will show you briefly, and others. They are equivalent, or better said, they provide exactly the same trajectories, but they may provide different velocities, but all of them within the same accuracy. The Leapfrog method is equivalent to Verlet, but it is even easier to derive. It's enough to realize that if I take two positions of a particle that differ in a short time step, like for example from here to here, then if I divide this by the time step, I'll get the average velocity during this interval. But I can say that with certain precision, this average velocity is the same as the velocity at the center of this interval. So I can write this approximate formula. And the same I can do for acceleration. The difference of velocities between two times divided by the time step is the average acceleration, and I can say that it will be the acceleration and the center of the interval. And you can mention here that I use here the halved time step. That's because I have them here. And this equals the force divided by the mass. And again, in both above formulas, I'll start with the value which is in the future, here and here, and put it on the left hand side, and it gives me the algorithm for one time step that then I, as before, will repeat many times. That is, from this I'll get that the velocity at time plus half the step is the velocity by one time step in the history times the acceleration, which means this times the time step, and similarly for the position. And as before, I repeat this many times, maybe billion times for large simulations. This method is fully equivalent to the Verlay method that gives the identical trajectory. But there is a small problem. The velocities are at different times than the positions. So it is again related to the problem I have set. I cannot use this for the equations of motion that contain velocities in the right hand side. This method is called Leapfrog because in English Leapfrog is such an exercise. We can interpret these two equations using this chart. We have the trajectory going in this direction in time. I start with certain position, and using velocity that I know, I will go here. At this moment I calculate the new velocity from the acceleration that acts in this direction. So I calculate the new velocity, and if I know this velocity, I propagate in time. So it's similar, right, such an exercise with jumping. Now I will show you it's something like an extra, not the mainstream, how to prove that the Leapfrog and Verlay method are equivalent. This is the Leapfrog method. I will write the second equation twice in two different times. That's because I want to obtain the Verlay method, and it has 3 times in it. So this is the same, and I'll write this equation once more for t by 1 time step in the history. And I subtract both equations, and what I get is this minus this is here, this minus this is here, and here's the rest. For this I will use apparently this equation, insert it there, then I'll rearrange this r, I'll get this one twice, and this I'll get there too, and what I get is almost the Verlay method. This I'll take from here, and this is the result. That's it. We have a new method, and we'll use it for something simple, for astronomy. Planet revolution around a star, planetary orbit. We have a method, Verlay or Leapfrog, and let's apply it to something which has a known solution. It is a planet revolution around a star. We know that using Newtonian mechanics and gravitational forces, planets, trajectories of planets are ellipses. So what the Leapfrog method does. It looks like this is an ellipse, but if we watch closely, we can see that the perihelion has the so-called precession. The axis changes in time. So I leave it draw, but there is also a good news. The good news is that the energy is conserved. That is, the axis doesn't change. What is changing is only this precession of the perihelion, something like a phase error. If we used halved time step, the rate of this precession would be 1/4. That is, this error is caused by discretization of our system. Of course, I have not pretended that our method or the Verlay method is exact. There is an error, and this error causes this precession. But energy is conserved. Similarly, if we have a harmonic oscillator and use the Verlay method or Leapfrog, the frequency is inaccurate, and the error in frequency, similarly in this precession, is on the order of the time step squared. And one note you can mention here, this is with a plus, so it's some information that may be interesting, but it is not the mainstream. We can approach the problem of numerical solving of equations of motion from the other side. We have a very strong theory which expresses the classical mechanics not by velocities and position, but by momenta and positions, so-called Hamiltonian theory. And we can write operators, certain type of something that describes me how the system evolves in time. And using these methods, we have a better access to all properties like the total energy. Using this, we can derive yet another flavor of the Verlay method. It is called the velocity Verlay. It is equivalent to the original Verlay and to the Leapfrog. And there is a question why another method if we just reshuffle here some terms and get the same. That's because we can get more information. We can get the following property of such so-called symplectic integrators like the Verlet method. We can estimate the error in every step, and not only the error, we can derive that there exists a special total energy. Energy is called in these systems the Hamiltonian. This is the sum of potential and kinetic energy. So there exists a perturbed energy that is exactly constant with the Verlay method. And it means that not only is the method time reversible, but it is better. The total energy fluctuates around this energy predicted by this perturbed Hamiltonian. That is, for the Verlay method, or for any symplectic method, the total energy, which is the sum of potential and kinetic energy, this should be constant, but we have an approximate method so that our total energy is not expected to be exactly constant. It is expected to be better constant if we decrease the time step. Then, for symplectic method, the energy fluctuates around a constant. If we have a method which is not symplectic, yet it is reversible, then the error at every time may be positive and negative with the same probability. So if we draw three trajectories here, they may look like this. They have random noise. That random noise doesn't have a trend, doesn't have a drift. It doesn't go to positive or negative values, but it is larger, and in long times it will be proportional to the square of the time, because it accumulates small independent perturbations. But if we have an irreversible method, it would be a Runge-Kutta type method or certain types of predictor corrector method, then we would have the total energy which has a trend. It is generally wrong if we need good energy conservation, but usually we use a thermostat anyway, that is, we keep temperature constant, and such an error is easily swallowed by such a thermostat. So this is the end of this very short talk. Thank you for attention.